Hi, welcome to another video. In this video, I'm gonna provide a full explanation about ASTM D2887, a simplest method. All right, before we get started, please subscribe to my channel. I really thanks for your support. So let's get into this simplest method. This is a typical report that you want to generate at the end of your method, ASTM D2887. So the first one over here we call it the boiling point table, and the left column you have is something like the percentage of your sample, at how many percentage of your sample. In the right column you have the boiling point corresponding to that percentage. So basically something like, let's say this one, that means 30% of my sample has boiling point of 95.2 or lower. So that means if I bring the boiling point to 95.2, I should be able to collect 30% of my sample, right? So something like that. The second type of report, which is very common, is we call it cut point table over here. So the cut point table is a little bit different from here. It's like a range of certain criteria over here, whether it's temperature, carbon number, something like that. So you have a range over here, and you want to report how many percent of your sample in that range, right? A little bit different from this one. All right, so keep in mind of this typical report, because this is the final outcome that we want to generate in this method. All right, so let's get into the sample type of this method. This method covers a sample that have the minimum boiling point from 55 degrees, and that is corresponding to C5 or C6 and paraffin, which is pentanol in that sense, right? So the max FPP final boiling point is 538 degrees. That's corresponding to C44, C42, or C43. Okay, so this is the range of the sample, the ranges of the method that we cover. Well, as long as the sample that have the range over here, this method is okay to run it. The typical sample that you can run on this is diesel, where you have the boiling points may range from 180 to 360 degrees C. This data from Google, but I think it should be accurate for that. Okay, so one of the most important characteristics of this method is full illusion, or you can call it 100% recovery. Why do I need to say this one? Because it's very important in case when we get into the calculation at the end of this video. So let me move forward a little bit faster to explain to you why we say full illusion and 100% recovery over here. So let's look at this one back again one more time. The max boiling point is a C42 or C43, and let me show you the chromogram of the. This is a chromogram of the of this method, and this method is able to elute up to C44 and a little bit further over here, and because it can elute C44, but my sample only has C42 or 4C3 as the heaviest carbon numbers inside. So that means if I run my sample that's within this range of boiling point, everything in my sample should be able to get eluted from the column. So that's why I'm saying this method is full illusion or 100% recovery, right? So keep this in mind because this is very, very important for the calculation. All right. Okay, so let's get into the instrumentation. What do you need to have in order to run this method? Of course, you need to have auto liquid injector because your sample is going to be liquid. You want to inject the liquid sample into the inlet. What kind of inlet do you have? For Agilent, I would recommend you go for Coulomb column inlet, or we call it COC inlet. You might probably want to use MMI inlet, which is multi-mode inlet. But from my experience, COC provides more reproducible result and more accurate result compared to AMI. All right. For the next item you want to have is the non-polar column, which is a PDMS column, like HP1, DB1, something like that. Then you, of course, you need to have programmable oven to ramp up the temperature from low to high. Then you have an FID for detection of all hydrocarbons inside. Then sometimes you may want to have a cryogenic valve in your system as well. The reason, because it's not part of the scope of method, but let's look at this one. The mean boiling point is 55 degrees, which is C5, C6, but sometimes your sample may have a little bit of C4, C3, something like that, and it's only outside the scope of this method, but for some reason, sometimes we would still want to cover those C3 and C4 as well. So in order to do that, C3, C4, and C5, usually they are eluting very close to each other at room temperature. So that's why you want to have a cryogenic oven, cryogenic valve to bring down the oven temperature to sub-ambient temperature. Let's say it's 5 degrees or 0 degrees, something like that, to get better separation of those C3, C4, C5, right? Okay, but just in case that your sample does have those, otherwise this is just an optional item. Right. So I'm not going to go into a detail of the parameter of each of these item over here, because the main idea of my channel is to share with you guys about the more about data analysis, more about principle, the understanding, right? So I'm not going to into this one. All right. So the next slide, let's get into what reagents that you need to have in order to run this method successfully. The first one you want to have is we call it retention time mixture, or we call it RT mix, right? Retention time mixture. This one usually you prepare about 1% mass of it in CS2, which is carbon disulfide down here. Okay, for the purpose of this one, what you need to do with this one is it will need to contain the N paraffin from C5 to C44, which is, let's go back to this one for 1 second. Right here. Okay, you see that the mean boiling point C5 and max is C43 something. And so when you want to build your calibration table, you want to cover both the low end and the high end of your sample type. So that's why your retention temperature should have at least C5 as a minimum carbon number, and maximum should be C44. You may want to have a little bit more, but don't go too heavy, otherwise the column may not be able to elute it. But the point is you don't really need more than C44, because your sample will stop at C43 or something like that. So you don't want to have like C46, C48, anything like that over here. They may not be able to elute our sample as a condition of this method. So stop at C44, that's good. So there are a couple of commercial suppliers. They can give you this kind of mixture over here. One of them is Agilent, or you can go for a separation system. Both of them will show you this one. So you don't have to prepare this one yourself. Right. The next item, what you need to check in this retention time mixture, you want to verify the retention time of every carbon number that you find in this mixture over here. The retention time difference between let's say you make 2 runs for this retention time mixture, and retention time difference between C5 from run 1 and C5 from run 2. The difference should be less than 0.1 min. And for my experience, this is not a problem at all. For Agilent GC, where EPCs control the pressure and the flow rate, it should be very reproducible. You should not have any problem getting this kind of repeatability. All right. So the next item you want to verify is the resolution between C16 and C18. This is a requirement inside the method. Okay, so there is a formula to perform this one. I'll get into that in a second after this slide. So just keep in mind that you need to do this one. Okay, then the next one, you want to verify the detector response factor, where you take C10 as reference. So the reason why you need to do this detector response factor is because eventually when we process data, which I have not shown you yet, but I just tell you something upfront, that when you process your data, you assume that your response factor is the same for the entire chromatogram. So that means C5, C6, C7, C8, every carbon number will have similar response factor. So that's why you need to verify that before you are confident that you can do that, right? So I will show you how to do this one later on, just a few seconds after this slide. And then you have this boiling point. Once you have done all of this 1, 2, 3, 4 step, you are good to go with the last step, which is the final outcome of this retention time mixture, where you will build a calibration table. And the calibration table for this method is a little bit funny. It's not like the typical calibration table that we know of, like the error count versus the concentration. But in this case, we don't need the concentration at all. What we need to do with this is we will build a table between boiling point versus retention time. So typically, boiling point will be the y-axis, and retention time will be the x-axis, right? Okay, so the next reagent, you need to have a reference gas oil, but I think for the to make it clear, I'm gonna stop here, and I will show you how to perform all these steps before we get into reference gas oil to avoid confusion, right? Okay, so let's get into ChemStation, and I'll show you the data I have here. Okay, here I have, if you see, I have made 2 runs using the retention time mixture over here. And so let's get into this. Sorry. Okay, we need to verify these 4 points before we can build calibration table. So what I have done, I have prepared like an Excel template over here. So these four criteria over here, and then at the end you will build a calibration table down here. Okay, so let's get into one by one. The first step you want to verify is you want to verify that your retention temperature contains from C5 to C44, and this is very simple. Right? You just need to verify the COA and the chronogram coming from that retention temperature. So let me show you that. Okay, for retention temperature, usually it come in ampule like this, and then they will show you the chronogram of that the ampule that they have run from the map from the supplier, and they will show you exactly what carbon number they have in the in the mixture in the ampule, right? So you can verify from here. You have C5 away from here, and you have up to C44, and so that's miss the criteria from here. It's need to have C5 to C44. So the question over here is, let's say you see here you have C5, C6, C7, C8, C9, C10, 11, 12, 13, 14, 15, 16, all the way until C20 over here. So every carbon number is present from here. But from here onwards, you don't have C21, you don't have C22, C23, you have C24. Or same thing over here, you don't have C25, C26, C28. So the question is, do we really need to have every single carbon number from C5 to C44? All right. So the answer to be honest, the answer is yes and no. So yes, why is yes? The more carbon number you have, the more accurate it will be. So that's the first thing we have to emphasize over here. The more carbon numbers that you have in your calibration mixture, the more accurate your data will be. Okay, but here's the point. When we say no to these requirements, that means you don't need to have every single carbon number, because eventually what you need to do is you think about building a calibration table. Let's say you do a normal typical calibration. Let's say you want to build calibration from let's say 10 ppm to 100 ppm, right? You can go from the first level probably 10 ppm, the second level probably 20 ppm, then the third level maybe 50 ppm, and then 100 ppm, right? Something like that. You don't need to go like 10, 20, 30, 40, 50, 60, blah, blah, until the end. You don't need to go something like that. It's a lot more. Of course, it's more accurate, but it's not necessary, right? So the same thing we apply to this retention temperature over here. You don't need to have every single carbon number, but it's good to have, but it's not a must, right? So you want to have as many as possible, but you don't have to have every single carbon number. So to answer that question is yes and no, right? All right. So most of the time you just accept to whatever your supplier can provide to you. You don't have to spike in. Let's say in this case you don't need to spike in C22, C23, something like that. Right? This is good enough for you to build your calibration table. All right, so that's the first criteria that we need to verify. The second criteria that we need to verify is, let me go back to this one, and let me show you this. Right, second criteria is that the RT difference between two runs is less than 0.1 min. And what you need to do is very simple. You just need to overlay two chromograms in CAM session. You should be able to do that. Okay, so here I have two runs over here, run one, run two. What I'm going to do, I'm going to overlay these two runs like this. And then I just need to scan through every single peak, something like this. And I want to verify whether the retention time between my two peaks whether more than 0.1 minutes or not. And I say if we are using Agilent Technologies EPC COC, it's very, very reliable. So retention time should not be that big difference. So if you look at this one, is the first one is 0.888, second one is 0.890. So that is only 0.002 difference. It's much, much smaller than 0.1 minutes. So what you need to do, you just need to scan through every single peak over here. And from my experience, that should not be a problem at all. Right? You should not run into this kind of problem any single time, right? Right. So if you look at here on the way up to C44, very repeatable. You should be good with that one, right? So this is the second step. So the next step, you want to verify a resolution between C16 and C18, and the criteria is resolution should be more or less should be at least 3. Right? So the formula that if you go through the method ASMB28A7, the method will be showing you the formula looks something like this. So T1 and T2 are retention time, and W1, W2, and W1 is basically the peak width at half height of the two peaks. So what you need to do is you have C16 and C18 over here. You want to key in the retention time of these two, and you want to have the peak width of these two. So let me show you how to do that from ChemStation and using Excel over here. All right. So first of all, because they are repeatable, we just need to look at one of them, right? Okay. Then you want to zoom. You want to zoom out a little bit to see where they are. Okay. But before, you see over here, I can identify this as C16 and C18 over here. But when you first started, you may not know where they are, right? So that's a very good point of. Actually, it's a very good question to ask. Uh, let me show you the beauty of this supplier, right? So they will not only give you the ampule that contains C5DC44, but they also give you the chromogram, something like this. So you have some kind of like a sense of where your peak should be. So you have something like, we call it markers. So in this case, you see C12 is probably a marker for your chromogram. So when you run your this mixture on your system, you get a peak somewhere here and it's much higher than the rest, you know that one is C12. Then from there you can work back to C11, C10, C9, C8, blah blah. Then you work forward from here from C12 over here, and then you can see the distance between. One of the beauty of not having every single point over here is you want to have a distance over here. So you see the distance between every carbon number from here is quite short over here, but the distance from C20 to 24 is much bigger. So the gap is much bigger over here. So when you see a big gap from your chromogram, you know that is C20 and C24. So this is something like some markers for you to identify the peaks from your chromogram, right? So this is a very beauty, the beauty of having this chromogram, right? So from there, you should be able to identify your peaks, basically something like this. And then once you have identified everything, focus on C16 and C18, which is here. And then what you have to do is you just copy the data from ChemStation over. So C16, which is 8.103. Let me scroll down here. Okay, 8.103 down here. So the retention time, of course, is 8.103. You can enter over here, 8.103. And then for C18, the retention time is 9.118. 9.118. Then for the peak width at the half height over here, remember this is the peak width at the half height, and that is exactly the same number as the width in ChemStation over here. So you want to verify that one. So 8.103 right here, and that is 0.039. And 0.039 over here. Then for C18, that will be 9.118, 9.118 down here, 0.0401. So you just enter 0.0401. Then from here, you should be able to plug this number into the formula and calculate the resolution over here. And in this case, I'm getting 15, so that's much bigger than 3. So I'm good with this criteria, right? So that's a very simple way to do that. All right. The next criteria you want to do is you want to verify a response factor. Let me show you one more time. Okay, the next one is verify a detector response factor and using C10 as a reference. So again, the idea why you need to do this one, because eventually when you process your data, I will show you that when we go through the reference or the sample, you will assume that the method actually will assume that the response factor for the entire chromogram is the same. So you want to verify that one. So here you have these are the carbon number that you have in the retention time mixture, and it's actually cover more or less the full entire chromogram, right, starting from C5 all the way to C44, right? So the criteria for this one is it has to be the relative response factor should be from 0.9 to 1.1. So how to do that one? Okay, the first we want to do is you want to have the amount or the weight of this individual carbon number that you get, or either you prepare yourself or you get from supplier. You should have this number. So let me show you one of that. Okay, for the retention time mixture, not only they give you the chromogram like this, but they will also give you this kind of like what's the amount, the weight of in every individual compounds that they added into the mixture, right? So you have all this number. What you have to do is just simply key in all those number into this amount column, right? So the next column is the error count column. So for the error counts column, what actually that is inside calculation from here. And once you run this one, you can simply print a report. You can also get the error counts from here, or you can also get the error count from here. You see like C5, what's the error count from here? All of this number. Then you just need to transfer all of this number all the way into this column over here. So I already have those number over here. I didn't show you here, but let me bring them up. Okay, I have those number over here. So what I need to do, I'm going to copy all this number into this column, right? All right, so the next step is you want to calculate response factor, and for this one to work, response factor is defined as the amount divided by the error count. Right? You don't have to worry about whether this one is the unit of this amount, whether it's gram or milligram or percents. It doesn't matter as long as they are weight basis, so that should be okay. All right, so you have this one. I'm going to write the formula down on the way to perform the same calculation for every of this. And then the next item you want to do is the method asks you to use C10 as a reference. So what you need to do is C10 is over here. Let me highlight this. So this will be your reference. So what you need to do is, what does it mean by reference? You will take the response factor from every carbon number from here and divide by the response factor of the reference, which is C10 in this case, and you get something like this. And eventually I want to write the formula down, so I don't want this number to change because I want every carbon number to divide it by this C10. So I want to lock the row 26 over here. Let me add the dollar button over here. So that will lock row 26 for me. So I'm getting something like this. Okay, so this is all. Let me do like something like this. It will be easier for you to see. All right, something like this. All right, so what you do now is the criteria for this number is have to be from 0.9 to 1.1. So let me show you. You may see that these two are failing. So let me show you that one real quickly. So pass or fail. This one, let me do like this. So let me do a quicker one. I will highlight those that. So let's say 0.9 to 1.1. If they are within this range, we're going to have them in green color, right? So all of them passes except for these two, C5 and C6. So let me show you a reason why we very difficult for you to get these two pass. Okay, let's get into this retention temperature. So usually when you buy retention temperature, they will come in this form, is in an ampoule like this. And if you notice, those heavy hydrocarbon, something like C20 up to C44 over here, usually they are present as solid at the ambient temperature. So typically you will see a lot of like solid things inside the ampoule over here. So in order for you to transfer everything out, in order to perform this calculation, I mean the response factor calculation, you have to transfer every single thing inside the ampoule out to your valve, right? To your GC valve to prepare this mixture. And in order for you to do that, most of the time you need to heat up the valve a little bit so that you can dissolve those like C30, C40, something like those heavy things. They may be able to dissolve at a little bit higher temperature. So when you dissolve them at higher temperature and the moment you open, you break the ampoule to transfer everything out. Some of C5 and C6 already vaporize outside. So that's why you will see that C5 and C6, the response factor, usually a little bit higher. So that's why it's very difficult for you to pass these two C5, C6. But because this is a typical thing happening every time, even those experienced, they have no idea how to fix this problem. So it's very understandable for you just to simply accept this one, or if you are like a service engineer like me, you can explain this to your customer. They should be okay to accept this one. But the rest from C7 and the rest over here, they are very good. Actually, you see C7, C8 also a little bit vaporization over here, but the rest should be very good. You see, it's very close to 1, right? Okay, so that is the criteria why you need to do this response factor over here. So once you have passed off this criteria over here, so remember that you have a total of 5 different criteria over here. Actually, the first 4 are the requirement for you to come up with the last one. So once you pass on these 4, you are good to go with the last one. The last step is actually just to build a calibration table between retention time and the boiling point. So what you need to do, you need to have all carbon numbers listed over here. Then you can get the boiling point from here for the method. This is the table that I took from STMB 287. So you have the boiling point. Either you are dealing with Celsius degree or Fahrenheit degrees. You have both of them here over here. So in Asia, in general, we are using Celsius degrees. So that's why I'm using Celsius over here. Just key in all of them over here. And then retention time, where you get it? You just simply need to get it from ChemTension. And again, you have 2 runs over here because they are repeatable. It doesn't matter which one you select. So just pick one of them, and then you have a retention time listed over here. Just transfer this number into this retention time column over here, and that's how you get the boiling point calibration table. Let me delete this one for a second, and then I'm going to transfer this number. I have them over here. Then let me just transfer this number into this column, right? So actually, this should be the last step for you to do this one. But if you look at the method, or if you use a commercial software, most of the time they will give you they will try to draw like a calibration curve for you. So what you need to do is just go to highlight this, go to insert, and you take this one, something like this. So this is a typical calibration table for this method. It doesn't look, it's quite linear over here. So this will explain why you don't need to have. So let's zoom in a little bit over here. Okay, so let's say this, you have this carbon number here, and then you have this carbon number over here, right? So even you don't have this middle point over here, if you draw a curve from the line from here to this point, it is still very, very good. So even you have this one or not, it doesn't really matter much, right? So that's a reason why we thought from the beginning that you don't need to have every single carbon number for this method, right? All right, so I think I'm going to stop at this in this video at this retention temperature because the time's running out right now, and I'm going to continue with another video about reference gas oil later on. Okay, so talk to you soon, and I hope you enjoyed this video so far, and let me know in the comment if you have any questions so far, and do not forget to subscribe to my channel. Thank you very much, and I see you soon. Bye.